Okay, we're ready to begin. Our first talk of this session is Gaoli Wang. She's going to be talking about Cryptanalysis 48-step RIPEMD-160. So, go ahead.
Thank you for your introduction. The complete function of the hash function RIPEMD-160 consists of two branches, a left branch and a right branch. Each branch consists of 5 rounds, and each round contains 16 steps. The chaining variables in left branch are denoted as xi, and in left branch. In right branch, the chaining variables are denoted as yi. Here is the step function. In order to compute xi, the inputs are xi minus 4, left rotation 10, xi minus 5, I minus 1, I minus 2, I minus 3, the message word, the constant, the rotational value. Fi is a Bohr function. The Bohr functions are as follows. In left branch, in round 1, it yields the Bohr function f1, and in the last round, it yields f5. In right branch, in round 1, it yields f5, and in the last round, it yields f1. Here is the sample of collision attacks on RIPEMD-160. It denotes semi-free start collision attack. Here is the classical approach to find a collision attack on MD series hash functions. The first step is to choose a proper message difference and get a collision differential path, which holds with high probability in the linear part, in the middle and the last steps. Then using part of the message for freedom to make sure the non-linear part hold with probability almost 1. There are some techniques to realize it, such as message modification. The linear part is verified probabilistically using the remaining message freedom. If applying classical approach to get collisions on MD hash functions, the first step is get 2 differential paths of right branch and left branch. Then derive 2 sets of sufficient conditions which ensure the 2 differential paths hold. They modify the message to fulfill most of the conditions on non-linear paths hold. However, it is difficult to get a collision attack on RIPEMD-160 successfully by applying classical approach. Here is a new strategy to find semi-free start collisions of this hash function. That means collision attack on the compression function. The first step, in the new strategy, the non-linear part is not necessarily in the first step. The attack procedure is as follows. Firstly, ensure the non-linear part hold with probability almost 1, using the freedom of the internal states and a few message words. Then we get some starting points. Starting points in here in left branch, starting points in here in right branch. Then compute backwards and get the initial values of both branches. And then in phase 2, we merge the 2 branches. That means we make sure the initial values of both branches equal. Using this new strategy, symmetry start on 24-step RIPEMD-160 dots. The phase 1 is to get 48-step differential paths in this. And this part is a non-linear part of left branch, and this part is a non-linear part of right branch. Then use the freedom of some of the message words and the internal states, the freedom of the internal states to make sure the non-linear parts hold with almost probability 1, and get some starting points in both branches, and then compute backwards and use the remaining freedom of some of the message words to merge. That means to make sure the initial values of both branches equal. From experiments, the probability of the last 6 steps is about 2 to minus 11.3. So the overall probability will exceed 2 to 80 for 48-step hash function. In this paper, we propose a symmetry start attack on 48 steps by using the same differential paths as in this paper. In phase 2, we use some message words, the freedom of some message words and the internal states to ensure the non-linear parts hold with almost probability 1. And it is noted that in this phase, the message words M1, M4, M7, and M16, M13 is unknown because the 4 message words are left to do merging. That means to make sure the initial values equal. Because M4 is here in left branch, it is corresponding to X36. That means X36 is unknown because one of the inputs M4 is unknown. Similarly, in right branch, Y29 and Y31 are unknown because the corresponding message words M4 and M1 are unknown. In order to improve the overall probability, the number of uncontrolled conditions must be decreased. So we have to compute some bits of these training variables. There are some conditions of the differential path on some bits of X37, X38, Y30, and Y32. In order to ensure these conditions hold, we must compute them in advance. So the problem is transformed to compute some bits of X37 and X38 under the condition that X36 is unknown. Similarly, to compute Y30 and 32, some bits of them, under the condition that y29 and y31 are unknown. We give an example to show how to add some extra conditions and compute some bits of them. Here is an example to compute y39. In order to compute y30 to 20, because there is a condition on this bit in the differential case. In order to compute it, we need to compute y39. Here is y30, the step function of y30. The broad function f4 is here. y29 is unknown. It is obvious that if we add the condition y27 equals to 0, then we can compute the output of f4. However, if all the 32-bit value of y27 equals to 0 is added, it will waste too much freedom. At last, the 9th bit of y30 can be computed as follows. It is equal to the 9th bit of this expression. In this expression, all the inputs are known. The reason is as follows. Firstly, we adding the conditions, the 3 conditions. Then we can get bits 23, 24, and 26 of f4 can be computed by this expression. Here, there is this condition y27, 50 equals to 1 is a condition of the differential case. So we can't get the 25th bit of f4. We denote R1, T, R2, Q1 as follows, and add these conditions. Then we can get R1I equals to TI, I equals to 24 and 26. Because there is no carry from bit 23 to 24 and from bit 25 to 26 when computing R1. That means we add the conditions. The purpose of adding the conditions is to know whether there is a carry. That's Q1I can be computed and Q17 equals to 0. Then add these 2 conditions, and we can get that there is no carry from bit 8 to 9 when computing this bit. So this bit can be calculated correctly by this expression. The experiment confirms the above computation. By computing some bits of the variables, then we can use message modification to make sure the conditions on these bits hold, and then the overall probability will be improved. Here is the second problem considered in this paper. It is about the sufficient conditions of the differential case of RIPEMD-160, because it's the step function is not a T function. The step function can be abbreviated as follows, and this one, xx prime. If here is left rotational. If b prime minus b equals to 17, the 17th bit of b prime equals to 1, the 17th bit of b equals to 0, a prime minus a equals to 2 to 31. Then x prime equals to x is not necessarily hold. The reason is as follows. When the difference of b prime at c and b at c propagate to the 18th bit, then the difference of the two values is not necessarily equal to 2 to 31. In order to get sufficient conditions of the differential path, that means to ensure the modular difference and the bit conditions hold. In order to make sure the module difference and bit conditions hold, Dom has proposed the method to calculate the probability of the differential path, including the modular difference and the bit conditions. Then Liu solved the problem completely and can give a set of sufficient conditions of the differential path. Then do message modification to ensure the conditions, ensure the differential path hold. When submitting this paper, this paper is submitted before Script 2017. We can make sure the modular difference hold when the difference of the internal variable is a power of 2. We'll give an example to show it. Here is the step function of xi. We denote R1 and R1 prime. Here, R1 is this expression. Let m prime minus m equals to 2 to 30. If R1 prime minus R1 equals to 2 to 30, then xi prime minus xi equals to 2. We want to get xi prime minus xi equals to 2. So if it is not equal to 2, we can do the message modification. If it is not equal to 2, we know that this expression is hold. That means R1. That means R1 is larger than R1 prime. There are many methods to do message modification. One of them is as follows. By this message modification, then we can change the most significant bits of R1 and R1 prime. Then we can get xi prime minus xi equals to 2. So the modular difference can be held by the message modification. The result is that the complexity of semi-free static collision attack on 48 step RIPEMD-160 is about 2 to 76.4. So the conclusion, firstly, can compute some bits of the chaining variables under the condition that some of their inputs are unknown. They present some insights of the sufficient conditions of the differential path, or to make modular difference hold, and get semi-free static collision attack on all steps. Thank you very much.
Do we have any questions? Okay, if nobody else wants to, I will ask a question. We saw the invited talk this year. We saw that a lot of these calculations people do to try to figure out how difficult it will be to find a collision turn out to be more complicated when they implement them. Actually finding it is very hard. I'm curious, what did you do to verify as much as you could that your attack would really work? Like, did you run computer simulations or something on parts of it?
Oh yes. The code is public on the GitHub.
Okay.
Web. Yeah, in our paper, we can find the website.
Okay. Did you do tests on like parts of this to make sure that the attack would work as far as you could? I know you can't do it to the 76 attack, so.
No. We have 76. Of course, we can't verify it. Firstly, we have verified that we can compute. We indeed can compute some bits of xi under the condition that xi some inputs. For example, we can compute x72 under the condition that x76 is unknown. We have verified all of the induction. And secondly, we have verified the message modification process and ensure that after compute some bits of the variables and do message modification, then the probability of the differential case is indeed the same as our theoretical analysis.
Okay. All right. Thank you very much. Thank you.